Welcome back. So in today's video lecture, we will look at the molecular interpretation of surface tension. So we will understand the role of surface tension when we want to determine the work required to pull the molecule near the interface, to the interface, right? So we have a couple of equations, famous equation proposed by Girifalco and Fowkes, right? So, but that involves the use of the London dispersion force. Because it involves the use of London dispersion force, we will also look at along the line. We will also look at other types of physical forces as well. So in today's video lecture, we will look at the different types of physical forces, in addition to the London dispersion force, and we will look at the Girifalco-Fowkes equation to understand the surface role of surface tension from the molecular perspective. Let's begin. Yeah, so as just now we described, so we will understand the different types of forces because we want to know what is the London dispersion force. But as we talk about London dispersion force, we can also look at the other types of forces as well. So let's first start with the hydrogen bonding. Okay, let's understand what is hydrogen bonding, and we have metallic bonding, and we have London dispersion force, and we also have dipole force, right? So first let's look at the hydrogen bonding. So hydrogen bonding exists. There are a couple of the two types of hydrogen bonding that from the molecular perspective. One is the intermolecular hydrogen bonding. Here, the hydrogen bonding exists between the molecules, right? Two different molecules. The other type is the intramolecular hydrogen bonding. This happens within the molecule. Okay, it shares the hydrogen bonding within the same molecule. Okay, so we'll see. Let's take an example of the hydrogen fluoride. Okay, so how the hydrogen bonding takes place in this case is you got hydrogen and you have fluorine. Because it has got number of valence electrons, that is 7. So it hawks electron from the hydrogen so that it can complete its valency, right? So because fluorine is highly electronegative, okay, and the electron cloud, because it hawks electron from the hydrogen towards it, the electron cloud will shift from the hydrogen to fluorine, and the probability of electron cloud seen in the fluorine end will be high. So because of which the fluorine will gain net negative charge, whereas hydrogen will gain net positive charge. Okay, and because of this hawking tendency, fluorine will always gain net negative charge, and hydrogen will gain net positive charge, and there exists electrostatic attraction between these two atoms within the same molecule, right? And this is one type of hydrogen bonding. So there are some examples for intramolecular hydrogen bonding. So this hydrogen bonding is very crucial in determining the physical properties. You can take an example of the let's say if you take an example of intramolecular hydrogen bonding, let's say ethylene glycol, okay, and intermolecular hydrogen bonding, the example that we can give is water, right? It's the simplest example of intermolecular hydrogen bonding that exists between the molecules, right? Different molecules, okay? So you can understand the role of hydrogen. If you look at the hydrogen sulfide, and the water itself, because of the hydrogen bonding, okay, in the water molecule, you can see that the physical property is drastically changed, right? The boiling point of H2S and boiling point of water, they are significantly different. It is because of the presence of hydrogen bonding. Okay, so this is one type of physical force. The other one is metallic bonding. So this exists between metal atoms. Okay, so usually these metal atoms are covered by the sea of valence electrons. Okay, and there will be, because of the delocalized sea of delocalized electron, metal atom will gain positive charge, and there will be the attraction between electrostatic attraction between this metal cation and the delocalized electrons, due to which you can expect metallic bonding between the metal atoms. Okay, this is another type of physical force, we can say. Here, this London dispersion force, this is always exist, no matter whether the atom is charged or neutral. Okay, because this London dispersion force is part of van der Waals force, which we will see in detail when we cover the module 4. Okay, so this London dispersion force is due to the electron fluctuation, the fluctuation in the electron density distribution. So because electrons are constantly jumping around, okay, constantly jumping around, there exists difference. There will be density. There will be a fluctuation in the electron density distribution, which will result in the net positive and net negative charge, because there is the electron density distribution is constantly changing. That will actually cause the atom to gain partial positive and partial negative charges depending on the cloud of the electrons, right? That are constantly jumping around. So you can expect, because this atom gains partial negative and partial positive, there can be electrostatic attraction between positive charge and negative charge, due to which you can expect the physical force between these neutral atoms, that is due to London dispersion force. So this type of force is called London dispersion force. You also have what is known as permanent dipole interactions. This is also part of van der Waals interaction. Okay, so the beauty of this interaction, if you see, the major, it is mainly due to the difference in the polarity, right? So this is usually the case for polar molecules. Okay, so you look at these two chemical compound, one is propane and the other one is acetaldehyde. Although the molar mass of these two chemical compound is same, you see this the physical property, let's say boiling point, is drastically different. Is because of the polarity, right? So dipole interaction, permanent dipole interactions. So this happens because in this case, this molecule has got oxygen atom, which is highly electronegative atom, so which will hog electron from the hydrogen, right? So because this polarity, the dipole moment, the dipole moment shifts towards the oxygen atom, because it hogs electron, right? So this end will gain negative charge, and the other end will gain the net positive charge. Okay, due to which you can expect electrostatic attraction between the molecules. So this is also one of the van der Waals forces, which we will cover in module 4. Now what we will do is we will try to understand. So what we have to do is our objective for today's lecture is, okay, let's say if I got one molecule here which is type A very near to the interface, there's another molecule here which is type B, okay, and you also have a molecule, you also have molecules in the bulk, right? The molecules in the bulk, these molecules are always surrounded by the neighbors, right? Neighboring molecules. So you can expect the interaction, from 360-degree angle. So you will have interaction everywhere, okay? And it is very difficult to separate the molecule from the bulk. Whereas here, you have the molecule very near to the interface, type A molecule and type B molecule. So there can be interaction between these two molecules as they are very near to the interface. Okay, so if A-B interaction sometime can overcome the A-A interaction, okay, in such case you can expect that this molecule can be pulled towards the interface, right? So this is the the objective. So what is the work required to, so this Girifalco equation is going to tell us about what is the work required to bring this molecule to the interface and form the interface, right? So in such case, so how it can be defined is, so we know the Girifalco equation, okay? So it says that so you need to calculate individually, that is work, okay, required to bring the molecule A, which is nothing but, gamma A. So why gamma A is because there will be interfacial surface tension, right? So one has to supply force equivalent of that so that this molecule can overcome the surface tension which is acting downward and can be brought to the interface, right? And in addition to it, you also have the interaction, right? That is due to A to B, right? A-B interaction. So this energy is actually a bonus for us because this is available naturally for us. So you don't need to supply this energy. So you can subtract this energy so that you can understand what is the energy required to pull this molecule towards the interface. So this is one way, right? So this delta E is associated with the London dispersion force as we described, right? When we talked about the various types of forces. So this is actually given as the geometric, this is described based on the geometric mixing rule. That is nothing but phi A gamma A and pi B gamma B. So this is actually different from the general mixing rule we often employ, that is pi I gamma I, because so in general this geometric mixing rule found very suitable for this kind of an application. So that's why this was proposed. Geometric mixing rule was proposed. Okay. So if I have to use the same for bringing the molecule A to the interface, then we have to use, we need same work to bring the molecule B to the interface. So that is nothing but gamma B and delta E AB, right? AB. All right. So what is the total work then? So total work is going to be the work A and work B, right? So which means that you have gamma A plus gamma B minus 2 root over phi A gamma A, right, into pi B gamma B, right? Right. So this is also denoted usually as gamma AB, okay? Yeah, it is interchangeably used. You can also use work total or gamma AB. So this is why Girifalco equation But folks approximate this as the following way. That means that is the work total is nothing but gamma A plus gamma B minus 2, okay, root over gamma A dispersion, gamma B dispersion. So in this approximation, you need not worry about the pi A, pi B component, right? Because in his approximation, he uses the London dispersion force based on his proposed method. So he has proposed the gamma AD and gamma D for several molecules based on his proposed method. So the advantage of this method is the gamma D is same as gamma for hydrocarbon, okay, for hydrocarbons. So we will see when we try to solve the problem in tutorial section, okay. So now we know that work total, okay, of gamma AB is nothing but gamma A plus gamma B minus 2 gamma AD gamma BD, okay. So this is our Girifalco-Fowkes approximation, right? So we will try to solve one problem as part of tutorial today, and so then we will use this equation and try to solve the problem, right? Yeah, so here we have got a problem where we need to understand the Girifalco-Good. So what we saw right now is the Girifalco-Good Fowkes equation, okay? So here, so we have been given the interfacial tension, right, for octane water, octane mercury, right, and we got water mercury. So what we are asked to find out is the gamma D for water and mercury, right? So let's understand this. Let's calculate this gamma D for water, and I leave it to you to calculate. Sorry, we'll calculate gamma D for mercury. You can calculate gamma D for water yourself. So now we know the equation, that is gamma AB, which is nothing but gamma A plus gamma B minus 2 root over gamma AD and gamma BD, right? So let's take the octane problem. Here we have the extent is octane mercury, okay. So and then we can try to solve the gamma D for mercury. So for octane mercury, we know the equation, that is 375, right, millijoule per meter square, okay. So let's use that, yeah. So we know this one, this is 375 octane mercury, and octane is 22, right, plus mercury is also given, if I am correct, it is 465, I think this is 465 minus 2, and so since we said gamma D is also nothing but gamma, you can take as it is, this one as it is, so which is 22, right, okay, into, and this we need to calculate, right, okay. So in this case you can calculate, then so we have this one gamma B D, okay, 1 by 2, right. So this you can say that 375 minus 22 minus 465 divided by, you have 22 into 2, so 22 power 1 by 2, right, yeah, into 2. So you can check, I think this is simply 140 millijoule per meter square. You can check this one, okay. Similar way, you can calculate the gamma T for water, right? So that I have given to you as an exercise, okay, for you to do yourself. We will stop here. We will continue from the next lecture. Thank you.